Okay, so there's been a lot of talk that we had on two-party secure computation. I won't define it. We all know what Yau's garbled circuits are. I will not define that. What we're going to be interested in is we're going to be interested in considering RAM analogues of garbled circuits. So we want what Yau gave for garbled circuits, we want it for RAM programs. So let me define the problem a little more precisely. We have a user, and he has some program P and an input X. So think of this program as a RAM program, just like Yau had as a circuit. And this user wants to send this program and the input in some garbled form. So he wants to send garbled program and the garbled input X, denoted here in red. So this is in the clear, this is garbled, such that the server can learn P of X, the output of the program, on this input in the clear. Okay? So Yau gave a solution for the setting of circuits, but for RAM programs, if you started with a program P, say of running time T, and you wanted to use Yau's solution, then the size of this garbling, which will result first by taking this program, first converting it to a circuit, and then generating a garbling, would grow with size a cubic in the running time of the original program, up to log factors, ignoring log factors, which is a substantial hit in performance. But we are interested in even a more ambitious goal, which is so in particular here the communication complexity, which is the size of the garbled program, and the computational complexity of both the user who generates this garbled program and the server who computes on it grows with T cube. But as I said, we are interested in this more ambitious goal of sublinear effort in communication. So in particular, we have a user who has this huge database, what Tal talked about as big data, and this user wants to send this huge database to the server in an encrypted form, so that server does not learn what the contents of this database are. And at this point, user has a sequence of programs. So let's say first program PI with an input XI, that he would like to run on this encrypted database that now rests with the server. So when he runs this this program on this with this database on this input, he should learn the output PIXI, depending on what this database is. And as this computation is performed, so the color of okay. So as this computation is performed, this database changes. And as this database changes and the programs, more and more programs are executed, we want those programs to be executed on the updated database. Okay? So if you were to use garbled circuits in this setting, then the size of the amount of work that the user has to do per program, also the communication complexity as well as the amount of work the server has to do, needs to grow with the size of the database. So in particular, the circuit must take in as input the entire database in one shot. Okay? So for every program, you'll have to communicate that. What we would instead like to do is that the first message in which the user stores this encrypted database, we want the size of this garbled database to grow only linearly in the size of the database. And then secondly, we want the communication and the computational cost for each specific program to grow only linearly in the running time of that specific program. Okay? So here the tilde hides polynomial factors in the security parameter and the polylogarithmic factors in the size of the database, the running time, and so on. Okay? So this is the problem. Is the problem clear?
Sorry, I have one question.
Yes.
The second thing, the computation goes with the running time?
Yeah.
So the user also knows the database?
No, the user once shipped the database, now remembers nothing about the database.
What if the running time depends on the contents of the database? Like what if the first bit...
So for now, think of the setting where you know an a priori bound, and we're going to have that. If you want to have input specific running times, you can have solutions for that, but we're not going to talk about that in this talk. Okay? Any other questions? Okay, so this is what our user wants. So this is, if you were to think about an example, let's say this database is, the record of all the terrorists that exist or all the cryptographers that exist in the world, and you wanted to do binary search on them, then the amount of work that is done per program is logarithmic in the size of the terrorist that probably is larger than the number of cryptographers in the world. So you don't want this communication cost to grow with the number of cryptographers in the world, just logarithmic in the number of cryptographers. Okay? So there are two kinds of security notions that I can define. The first is the full security notion, which is sort of what we are interested in, which says that the server should learn nothing at all about the database or what's happening except the output. Okay? The second notion is the unprotected memory access, where the server, so this program runs in time that is much smaller than the size of the database. So it cannot read the entire database. It can only read parts of this database. So in making these choices, it reveals to the server what parts it's reading, and we're okay to leak what parts it's reading. Okay? So this might, this reveals some information. For the rest of the talk, I'll focus on this notion. The reason is that if you took this notion and plugged in oblivious RAM by Goldreich and Ostrowski, then you get a full security solution. So that sort of follows in a relatively black box way. We'll need some additional ORAM properties in special settings, but we will mainly focus on the unprotected memory case. Okay? Is that clear? Okay, so what is the landscape of results on the setting of Garbled RAM? So the first construction was proposed by Lou and Ostrowski in Eurocrypt 13, and the result sort of relies on a somewhat complicated assumption. In short, you cannot reduce the security of the construction to a simple computational assumption. So sort of has a flavor of circular, secure, complicated assumption. It was improved by Gentry et al., where they got a construction based on IBE, and for Garbled RAM, and a second result which was based on one-way function, but did not get the kind of efficiency guarantees that I promised here. This talk, we have an upcoming paper with Lou Ostrowski and Scafuro, where we get the result that's just based on one-way functions. But what's very crucial in all these results is that they make a non-black box use of the one-way functions. In particular, you cannot model the one-way function that's being used as a random oracle in implementing these constructions. So they take the code of the one-way function, which is then again garbled inside the construction. Okay? So, yes?
I didn't understand the Gentry et al. They already did one-way function, but
no. So it had two results. One was based on IBE. That got exactly the kind of efficiency that I said. And then there was another result based on one-way functions, but it did not get the kind of efficiency that I aimed for. It had an additional loss, and so when you're sending the garbled program, the size grew additionally with n to the epsilon, where n was the size of the memory for some constant epsilon, right? So I'm not going to be focusing on these results. The focus of this talk is going to be how can we move forward and base constructions just making only black box use of one-way functions. And this is a qualitative efficiency improvement. In particular, in this construction, it's also based on just on one-way functions. The improvement is in the sense that in this result, the communication cost, for example, of the protocol does not depend on the computational efficiency of the one-way function that you're using, as an example. Okay. As a side remark, I will not talk about succinct Garbled RAM constructions that are based on I/O. So those results are very interesting, but they're not the focus of this talk. And we're going to get security here based on a much weaker assumption, namely one-way functions. Okay.
What do you mean by succinct?
So succinct, I mean is, so someone has to do the work. So computation is happening, right? So in the setting of succinct, the server does the work. The user's work is going to become independent of the running time of the program, as well as the communication cost. Okay? So in particular, only the server does the real work. Everybody else just watches what the server does.
So in your result, you have a much weaker assumption, but the client does the work.
Yes, yes. So both the client and the server do work proportional to the running time as well as the communication cost, but the dependence is only in on one-way functions. Okay, so outline for the rest of the talk, I'll start by describing what the RAM model is. Then the core thing that I want to convey in this talk is what is the technical bottleneck that comes up in realizing a black box construction. And to explain that, I'll give you the Lou Ostrowski construction as the kind of ideas they had. And from there on, I'll give the high-level idea of the black box construction that we have. Okay? So let me start with the RAM model. So we have this external memory. The CPU takes various steps. So CPU has a state that it takes as input. It reads a bit from memory, outputs the next index that it's interested in reading, passes on the state to the next CPU step, reads this next bit that was intended, and so on, and this process continues. Okay? So this is the RAM model. I'm going to ignore the writes here. So sometimes a lot more and sometimes much less work needs to be done to handle the writes. But for sort of the whole talk, we'll now worry about writes, and we'll just look at the RAM programs that do just reads. Okay. So the first step in the Lewis-Roski approach was to take this, if you have the running time, you take each CPU step and give a separate garbled circuit for that step. Okay? So that I can just do by garbling each CPU step. I also need to somehow encrypt this memory and then enable these reads. So as I said, we're only going to focus on UMA security, so I'm not trying to hide the read patterns. But as I mentioned, we can get rid of this limitation by using ORAM. So what I'm going to do is, how do we do these reads? I'm going to do it in sort of explain it in two-step process. The Lewis-Roski approach. The first is in garbling this memory, and the second is to generate translate tables. So let me explain how Lewis-Roski garbled this memory, and then explain how reads happen. So the approach for garbling is sample a PRF key K, and if location I of the memory contains a bit BI, then the server is provided with a PRF evaluation on I, BI under key K. Okay? So this is just an encryption of this bit in some fancy form. Okay? Is that clear? So very simple what's happening here. Next, we want to generate a translate table that will equip reading at this step. So these are garbled circuit. This circuit needs a label for it to know what the read value is, and how is that going to happen. So in particular, this garbled circuit can output a value j in the clear that it needs to be read. And this garbled circuit has two input labels, S0 and S1, and it needs one of them to proceed. In particular, it needs SBJ, S subscript B subscript J, right? How are they able to enable it? They embedded the BRF key in each of the CPU steps, and the first step, for example, could output an encryption of PRF KJ0, encryption of S0 under this key, and an encryption of S1 under this key. Okay. Now, if the memory, look at the jth memory location, it contains the PRF key corresponding to one of them. So you will be able to decrypt only one of them, enabling you to obtain SBJ, and move the computation forward. Okay. So it's sort of very clear that this CPU step is inherently non-black box, because it's computing a PRF inside itself, as well as doing an encryption of S0 under that. Okay? So this actually, it seems like a really, so the other constructions which are follow-up, even the final one which is based on one function, sort of inherently have this property that there is some PRF evaluation happening inside the circuit. So this is the key technical bottleneck that existed in the previous constructions. In particular, if you were to think, if there is a server, I have to keep my data with it. It has to be encrypted in some way, right? It has to be encrypted in some way, otherwise it can read off that values. Now, if it's encrypted and I have a garbled circuit that needs to read these encrypted values, I must read the ciphertext and decrypt them inside myself to be able to use them. So it seems like we might not be able to go beyond this barrier, but sort of a cute idea works, and we're able to avoid this. So the high-level idea is that instead of having the garbled memory as ciphertext, we're now going to have the garbled memory as sort of a collection of garbled circuits with the data values hardwired in them. So this is sort of a high-level idea. In the next slide, I'll show a picture. It'll become clear. But sort of this high-level idea is good to build intuition. And a read is implemented by passing the control flow of the main program itself to the garbled circuit probe. So at some point in when I want to read a bit, I start the memory garbled circuits. The memory garbled circuits are huge. It's a huge collection. Depends on the size of the database. Some of those garbled circuits are going to be executed, and the main garbled circuit is going to be restarted with the read value.
So it's a kind of access?
Access, yes, exactly. It's like a subroutine call that you make. Something happens, and you get the information back. So let me describe that. We have two CPU steps, just like before. This CPU step outputs the location J that I am interested in reading, and what I want to enable is output SBJ. Okay, and my memory is going to look like following, or the garbled memory is going to look like a tree. I have a root garbled circuit. it has 2 children, and so on. The number of leaves in this tree is going to correspond to the size of the database itself. And in each leaf, I'm going to hard code 1 bit of the database. So in the root, I'm going to hard code the input labels of both its children and so on. When I want to read the location j, what this circuit does, it's going to have hard code in it. So right now I'm describing the solution for the setting where I'm only trying to enable 1 read. I'm looking at a program where I'm happy if I'm able to succeed in doing 1 read in a black box way. We'll then see how we can extend it to do more reads, but this sort of conveys the idea in a very nice way. So I have this location j. I'll start this root garbled circuit with inputs this location j that I'm interested in reading, as well as S0 and S1, the 2 input labels for the next garbled circuit. Okay. Now this garbled circuit has hard-coded in it the input labels of its 2 children. Let's say j was 2, so I'm interested in reading the bit b2. This guy can decide that it needs to go left to be able to read this bit. So this garbled circuit gets executed, and then the left child will be executed, and finally I'll be able to read this garbled circuit, which has the bit b2 hard-coded in it. With all this information on JS0, S1 being passed along down. At this point, this garbled circuit knows what b2 is and can output SP2, which then can be fed into the next step, enabling the next CPU step. Okay? Is this clear how 1 read is done? So the key problem with the solution is after you do 1 read, this memory is no longer useful. This guy is no longer exists. What is the next guy supposed to do when he invokes it?
What is the relationship between the nodes in the tree?
So the input labels of these 2 garbled circuits are hard-coded in this. And so each node contains the input, hard-coded in it, the input labels of its children.
In the and you just decide 0, 1 based on
yeah, I mean, it can be in the clear as well. It's a garbled circuit, right? Yeah. Any other questions?
So it emulates in a garbled way.
Yes.
Exactly how RAM programs
Yes.
in architecture access an index.
Yes, yes, yes. The idea for enabling multiple reads is to now, so there are a lot of technicalities here. I'll just give you the high-level idea. But the high-level idea is, though, instead of having just 1 garbled circuit, I'm going to have a sequence of garbled circuits. Okay? So the root is going to have a sequence of garbled circuits. Once the first garbled circuit gets consumed, hopefully the second one is going to replace it in some way. We'll see how. The question is, how many backups do we need, and how do we connect them? Yes?
Complexity of the encoding of D should have been independent of the computation.
It is going to be. So right now I'm only dealing with the case where I'm allowing for M reads, where M is the size of the memory. In future, so I did things for the case where I was doing 1 read. Now I'm doing for the setting where I'm doing M reads, and no more than that, where M is the size of the memory. Then I'll extend it to the setting where I will be able to handle arbitrary number of reads without increasing the size of the memory beyond being linear in M. Sounds good? Great question, thanks. So how many backups? If I was to take this program could access arbitrary locations in memory, and it could want to read the first location every time, and so I might have to give a large number of backups for the leftmost child, for example. What we're going to do is we're going to simplify this problem. We're going to assume that the memory access patterns are uniform. Okay? So this is not true about an arbitrary program, but once you compile it with an ORAM, it's still not completely true, but a starred version of it is true, which suffices for construction. And I will sort of focus only in the case where you have uniform memory accesses. Okay? If you have uniform memory accesses, then we're sort of at least ready to answer the first question, how many backups do we need? The first garbled circuit, the root level garbled circuit, we need, if you're doing T reads, we need T of them. For the children, we need T by 2 and so on. Right? So now that we have answered the first question on how many do we need under this assumption that we're going to focus on for the rest of the talk, how do we connect them? It's sort of a somewhat tricky problem. So let's see. If I went left, for example, right? So if I was going, this is the root node, and I go left, then this second garbled circuit in the root needs to replace the first guy. But it needs to have hard-coded in it the input labels of the second left child and the first right child, right? And, well, I could have also gone right. If I went right, then I need to remember the first left child and the second right child. So in effect, I need the second garbled circuit here needs to remember both the input labels of the first and the second left and the first and the second right child. And this number will keep growing as you go further. Okay? So the number of keys that need to be hard-coded in each circuit needs to keep growing. But hopefully not all, because we have assumed there is uniform memory access. Hopefully at some point we can stop hard-coding keys, and if you had a large enough window, it might suffice. Actually, it is not true, because even if you had t reads, with the noticeable probability, you'll have a discrepancy of square root t, and you need to remember square root keys. Okay? We have a sort of a cute fix around it, and the idea in our case is we're going to have a moving window, just as I sort of motivated. Yes?
Why can't the teeth layer always just discard the top one and always just do that layer?
If you did that, you will need t garbled circuits for the children, t for the subchildren, and so on. The growth is t times m then, it's not reducing. Okay. Did I?
I'm done.
Yes. Okay, I should be done. So I'll have a moving window. So for example, in this, which is the fourth root garbled circuit, I have a window of keys for the left children and a window of keys for the right children. And the next one will have a window that moves a little ahead. In order to make this idea work, what we need to do is have the number of garbled circuits which is slightly larger than the expected amount. So we have 1 plus epsilon times the garbled circuits that are sort of needed in expectation, and this gives us two guarantees. One, if I am lagging behind, so if I am I'm behind the window that my parent expects me to be in, then I can artificially consume garbled circuits and push myself in the window. And the other thing is, if I am already ahead, I would, by Chernow bound, not go beyond this barrier of 1 plus epsilon. We need this epsilon to be little of 1 for the scheme to remain efficient, but it sort of works out. Okay, so now that I've described a solution which sort of deals with m reads, now I need to deal with the case where I have more unbounded reads, right? Back to Abhi's question. So the idea for that is, I have to do that, but in sort of an oblivious way. I don't know what reads actually happen. I just know that they're sort of somewhat uniform. Given that, I want to be able to replenish memory, and the idea for that is I'll have a sort of a continuous replenishing mechanism. As I use the memory a little bit, I'll add a little more. But since there is a big enough buffer between the consumption and the addition, it doesn't matter which places you consumed. Does that make sense? So I have these queues for the root and so on. I'll keep adding garbled circuits to each of these queues. And at each step, I'll add the number of garbled circuits that I'll send with each garbled circuit will be proportional to the number of reads that specific garbled circuit makes.
So working overhead.
Yes, yes. And then there is a queue in the middle which ensures that the obliviousness is preserved. Any questions? Okay. So the security actually has a couple of other issues. I won't talk about how we solve them, but just to give you a flavor of the kind of techniques that go in. The first is the construction that I just described has a circularity issue. It's sort of somewhat similar to the original Lewis-Trotsky solution. The reason being that I have one garbled circuit, and the input labels of this garbled circuit are hardwired at multiple places. And to be able to invoke the security of an individual one, I need to get rid of all of them before I can do that. So this is some issue that we do resolve and need some care, but sort of an interesting issue that it comes up. The second is that in our setting, the garbled circuits are sort of not executed in a linear way. So one garbled circuit has its input labels that come from different sources and are provided at different times. So that sort of leads to other security complications. Okay. Okay, so let me conclude to make sure Hugo doesn't get too upset. A little is okay. So cryptography we have been doing cryptography for circuits for a long time, and we've done fairly well. But we should now move on to RAM programs, and really, I think there is a great scope for getting a lot of efficiency here, and this is sort of the right direction to pursue. Within RAM computation, typical solutions, for example, what Tal talked about, typically require large round complexity. In particular, the round complexity needs to grow linearly in the running time of the program. And the reason for not having a low round complexity has been this non-black box use of cryptography. And this sort of has been a barrier that whenever we tried to make things non-interactive, we had to sort of inherently use non-black box techniques. And this is sort of the barrier that we overcome in this result. I expect the many consequences of the techniques that we have developed. For example, in symmetric searchable encryption, we have solutions which are fairly efficient. They're very non-interactive, but they do not get the best security. The techniques that we have are asymptotically good, but they're not practical in any sense. But I do believe that we could extend them and get solutions which are which cross that barrier of doing better security and still remaining in the regime of practical or theoretically practical efficiency. Okay, so thanks.
Actually, I really liked to finish this workshop with that last sentence, really saying that we can unify these two parts of this workshop, the more theoretical one and the one trying to go more towards practice, and bring them together. I definitely believe so. One question? Very good.
Yeah.
When you refresh the memory, it seems like the garbled circuit has to make the garbled circuit to refresh the memory. So I don't see how you got around the...
We don't, the garbled circuit doesn't generate that. We just give, it's a queue, right? And there has to be a garbled circuit which is missing. I'll just give you that garbled circuit. Right? So the first time, for every read, I'll give you if I'm replenishing the ith time, I'll give you the ith, the number of garbled circuit that needed from the root to the ith leaf, which is sort of proportional to just logarithmic factors. Right?
Garbled circuits never generate other garbled circuits. Garbled circuits just have labels inside of them in their belly for other garbled circuits.
There's a lot of labeling.
Yes.
In this solution.
Yeah. Labels being passed and labels for labels of labels as well.
Okay, let's thank Sanjam and everyone in the workshop.